Good afternoon. All right. So, okay.
Hello. Good afternoon.
Hello. Hi,
Hello.
Ian. Hi, Sir Perry. Good afternoon. Yeah, so we're complete na as the panelists. And Doc Saloma can stay until 2:30. So, if it's okay with everyone, we can start na.
Sure. Yeah.
Okay. So, today we will have Gab Dizon's PhD candidacy exam. This meeting will be recorded for record purposes. And without further ado, I have to say who is the panelists. The panelists are myself, Dr. Reina Reyes, Dr. Cesar Saloma, Dr. John Rob Bantang, Dr. Ian Vega, and Dr. Perry Esguerra. And this is also open to students, other students, and members of the community. So we'll start with Gab's presentation, and then we will have the questions from the panelists. Go ahead, Gab. We can see your slides.
So good afternoon. I am Gab Dizon from the theory group, specifically now the data and computation subgroup. And for my candidacy exam, I will be talking about primordial black holes, particularly focusing on the wider aspects of it, on its formation, the growth, and some of the more relevant observational constraints that are being put into these objects. So the outline of my presentation is as follows. First, I will give a fairly brief introduction into what primordial black holes are and what they are in contrast to the more familiar astrophysical black holes. Then I will jump right into talking about the growth and formation mechanisms of the primordial black holes, although I will not go in depth in exactly each model, but more of the general sense. Information mechanism, clustering behaviors, the initial mass function, the initial spins, and the growth mechanism that I will be talking about primarily would be accretion. And then finally, I will talk about the observational constraints on the primordial black hole model. In particular, I'll be focusing on 3 different probes. First due to evaporation from Hawking radiation, the second from gravitational lensing, and finally, the hot topic would be being gravitational wave observations. So to introduce primordial black holes.
Sorry, Gab. Just if you're comfortable, you can also turn on your video so we can see you speak.
Okay. So primordial black holes in particular are basically, they're functionally black holes, but their formation channel is quite different from the astrophysical one. So primordial black holes are formed from the early universe, from early overdense fluctuations in the matter energy fields. So in contrast to astrophysical black holes, which are primarily matter-based, or at least we know them to be baryonic, primordial black holes are both matter and energy combined, and then you let it collapse very early on. There's no stars involved. And the different criteria may account for the formation of your primordial black holes, depending on whether it formed during the radiation epoch, very early on in the universe, or a bit later during the matter-dominated era of the universe. Now, as I mentioned, primordial black holes are fairly unique because they're not constrained by the known limits of stellar evolution, simply because they are not of stellar origin at all. As such, you can have a range of masses from around 10 to the negative 5 grams, or in solar masses, that's 10 to the negative 39 solar masses, to up to more than 10 to the 15 grams, or more than 10 to the negative 19 solar masses. Why I set the cutoff here at 10 to the 15 grams is going to be relevant later on, particularly in the PBH evaporation. but we will discuss that later. And finally, primordial black holes are of very significant interest because they are also possible dark matter candidates, and at the same time, they are also possible gravitational wave sources, both of which are fairly active topics of research right now in the astrophysics community. So let's get now to the formation mechanism. So the formation mechanism of primordial black holes is actually fairly simple from a physical standpoint. Since it starts at the early universe, the universe inflates, and the inflating universe overall has a flat and homogeneous Friedmann-Lemaitre-Robertson-Walker metric given by this equation over here. Now, your primordial black holes form from local dense, overdense perturbations over that background metric. And those perturbations generally have this closed spherically symmetric form, where K here is your spatial curvature, and it is generally taken to be positive. So your PBHs start forming from these overdense regions once you start to consider the density contrast between those regions and your background density. So the density contrast between the overdensity and the spatially flat background is given by this delta over here. So rho is the overdense region's density. Rho bar is the background density. K is the spatial curvature of your overdensity. A is the scale factor of the expansion, and H is your Hubble constant, which is both of which are dependent on time. For PBHs to form, you need to have a K greater than 0, which basically means that it's a closed universe and it is cut off from, well, you could approximate it as being cut off from the rest of the spatial universe. Now, this density contrast will evolve in time. And as it evolves, you will now have to check whether or not that overdensity will actually form into a primordial black hole or not. So the criterion for the primordial black hole formation is met when your density contrast at horizon crossing time. So to clarify, a primordial black hole usually is larger than the Hubble radius of that universe, considered in the closed metric over here. And then eventually, both the Hubble radius grows as time passes. And you will get to a time when the radius of your overdensity is going to be smaller than the Hubble radius of your universe. By that point, the approximation given earlier by this metric breaks down. And if your density contrast delta is greater than or equal to 1/3, then your overdensity is going to collapse into a black hole. Eventually then, at time of formation, so at the time that your black hole forms, your density contrast is expected to reach order of 1. So this is a rough outline of the formation mechanism. In reality, you could have a range of criteria for densities when your black hole starts forming, but in general, it ranges from 0.3 to around 0.6. And 1/3 lies well within this range. So that's it for formation. Then, once your black hole has formed, you will now start to ask the question, how are the other black holes around it? How is the distribution of all the PBHs spatially throughout your local neighborhood? And it turns out that generally speaking, your long and short wavelength modes of your primordial perturbations throughout your entire universe are uncorrelated. So what this means is that, okay, if your short wavelength modes correspond to your primordial black holes and your long wavelength modes correspond to your large structure perturbations, then in general, they're not going to follow each other. Which also means that your PBH initial spatial distribution is expected to be uniform, and the number density of your PBH distribution is expected to be Poissonian. However, there are models that will take into account that there are possible correlations with how the perturbations form. And if those correlations are non-zero, then you will get some clustering as well. Although I will leave people interested about it to check out Belotsky's paper, review paper on black hole clustering. Now, we've formed the black hole. We have checked how its spatial distribution is. Next, we can talk about how its masses are distributed all throughout as at each step of formation. So there are different models, and those models depend on a lot of things, such as the theory of gravity that you're using, etc., etc. But in general, if you're looking at an unclustered or a weakly clustered distribution, then you can model, or rather you can make a parameterization of your initial mass function that is model independent, and it can be written in this log normal form. So Zi here corresponds to the redshift at formation of your primordial black holes. M is the mass of the PBH at the formation. M sub C would be the characteristic PBH mass, or let's say the peak mass upon formation at redshift Zi. And finally, sigma here would be the width of your distribution. Some people, or rather some models, will only take a monochromatic distribution. But in general, if you want a mass tail, or if you want an extended mass function, you can start with this kind of distribution. Along with the masses, since if you're looking at black holes that are generally no hair, you will only look at the mass and spin. So there's also an initial spin distribution. But since primordial black holes, especially in the radiation-dominated era, tend to form in fairly spherical perturbations, their spins are generally fairly low. So you can have a characteristic value as an estimate for their spins, given by chi here. And it's generally like 10 to the negative 2 times this parameter over here, which is also going to be fairly low. Since gamma here will usually only range from 0 to 1. If you have a monochromatic distribution, this will be 1, and you generally will have no spins, but otherwise it will still be a fairly low quantity, dependent on the fraction of the dark matter, the variance of the density perturbations upon the horizon crossing, and then of course the shape of the power spectrum as well of your primordial black hole distributions. So now that we've initialized the primordial black holes, so we have their formation mechanism, we have their clustering mechanism, we have their clustering behaviors, we have their initial masses and initial spins. We can now talk about their growth mechanisms. Now, primordial black holes, just like most other black holes, generally have two formation mechanisms. One is through accretion and the other is through merger. We will first, or rather, we will only tackle merger for this talk because we will only tackle accretion for this talk because mergers in general are not really frequent events, and you can't really rely on them for growing your black holes unless, of course, they are fairly highly clustered.
Hello, Gab.
So in
May I interrupt for a while?
yeah po, sige po.
Can you move back a page? Sorry.
Sige po.
What is chi?
Po?
What is chi?
Chi po is the dimensionless spin of your.
All right, thank you.
So I forgot to mention, chi here will be your dimensionless spin of your primordial black hole, at least initially, upon formation. So moving on. So I will only focus on the growth mechanism via accretion here in this talk. And the main accretion mechanism and the main accretion formulation, at least for primordial black holes during the early universe, is given by the Bondi-Hoyle accretion rate. So MB here, MB dot here is your accretion rate. And it is dictated by one, the dimensionless accretion parameter, which this is generally where you chuck in all of the environmental parameters such as gas viscosity, cosmic reionization, Hubble expansion, etc. All of it is dumped into the dimensionless accretion parameter. MH would be the mass of the hydrogen gas around it. And then N gas would be the number density. The effective would be the effective velocity of your primordial black hole with respect to the background gas. And finally, RB here is your Bondi radius of accretion, which is generally dependent on both your effective velocity and the mass of your initial mass of your primordial black hole. So in general, what usually happens is that the larger your primordial black hole starts out as, the more efficient its accretion rate will be. So if you look at this figure over here, taken from De Luca's evolution of primordial black holes and refining observable spins, you will see that starting at around redshift 100, if your black holes start out with fairly high masses, so for example, the dark line over here, the dark thick line over here is 10 to the 5 solar masses, it will generally have a much better accretion rate, even going on to the modern era, or to the present time, as compared to a black hole that started out at, like, let's say, 10 to the 2 solar masses, 100 solar masses, where even during the early universe stage, it will be fairly inefficient with its accretion only up until reaching a certain point where it will start to accrete just like the rest of the higher mass black holes. Now, this is but one model of accretion, namely where dark halos, you assume that your primordial black hole has a dark halo closing that will allow it to accrete more matter efficiently over time. And then this model 2 over here corresponds to a particular model where at around redshift 10, you expect your black hole to still be accreting matter efficiently. Now, black hole accretion itself is a subject of study still, because in general, you do not know when or how efficient your black holes accrete matter after structure formation, even during structure formation. So there's this demarcation line over here that transitions from the dark halo side to the model 2 side. And essentially, model 2 here is assuming that your black holes accrete matter at a still fairly appreciable rate as you go into the present time. This paper has a model 1 to it, except model 1 assumes that accretion abruptly halts at this redshift. But I'm not showing it here because it's not really that relevant to discussion right now. Plus, they don't really have a image of it as well. So I've discussed the first part, which is on from formation to growth. So now I will move on to the current observational aspects that are being probed in studying, or rather in checking for the existence of primordial black holes. So the observational constraints on abundance that I will be talking about will be on first, the evaporation due to Hawking radiation. Next will be on gravitational lensing. And finally, I will talk about primordial black holes, the gravitational wave setting. So I'd like to talk about evaporation as the very first point because in general, due to the wide mass range of your primordial black holes, if you account for Hawking radiation, the lower tail end of the mass spectrum is going to be cut off simply because of the phenomenon of the theorized phenomenon of Hawking radiation. That is to say that your primordial black holes that are below 10 to the 15 grams, or rather around 10 to the negative 19 solar masses, would have already evaporated by the present time due to this Hawking radiation. So if you recall, Hawking radiation is simply defined as the black body radiation emitted by your black hole over time. And the time scale for that evaporation is expressed by this equation over here. Now, normally, if you have a stellar mass black hole, for example, M would be on the order of magnitude of a solar mass, if not higher. And as a result, the time scale for the evaporation is going to be way, way longer than the age of the universe. However, if you start early on in the universe, if you form early on in the universe, and you start out with a mass of around 10 to the negative 19 solar masses, you will get a evaporation time scale of around 10 to the 10 years, which is still well within the current age of the universe as well. So if you start out very early, that means if you start out fairly early and small, then chances are the black hole would have evaporated by now, assuming it doesn't accrete enough matter efficiently. Now, black holes more slightly massive than this will leave behind observational signatures simply because they're still evaporating. Rather, they're fairly close to evaporating into a burst of gamma radiation. Now, there are multiple studies concerning this effect, or rather the effect of PBH evaporation on the constraints. And it's fairly neatly summarized into this chart. So you can have multiple probes on evaporation. First would be the cosmic microwave background. So to explain the chart, the shaded regions here are all exclusions from the parameter space. So anything shaded is already excluded, is no longer really considered to be viable, to be a viable part of the, or rather to be considered as viable for your PBH abundance. So for this particular mass range, right, let's say from 10 to the negative 17 to around 10 to the negative 15, or 10 to the negative 17 to the 10 to the negative 16 solar masses, your abundances are constrained right down to around 10 to the negative 2, 10 to the negative 3 in fraction. So abundance here refers to the fraction of your primordial black holes that can be considered as dark matter. So what's this saying is that based off measurements that we have of the CMB, the gamma ray background of gas heating, specifically on dwarf galaxies and the 21 centimeter absorption line of hydrogen, along with the particle emissions, like let's say positrons and electrons, we can fairly confidently say that the fraction of primordial black holes within this fairly small mass range is not going to exceed around 10 to the 1, 10 to the negative 1%. So that's at least for the smaller primordial black holes. Now, another probe that's being used to constrain the abundance of your primordial black holes is gravitational lensing. So to recall, gravitational lensing is depending of your light from distant sources in the sky due to the gravitational effects of a massive body that's inserting itself in between your source and the observer. So if you have a source plane with a star that you're trying to observe, then there's a massive compact object like a black hole passing through it. Then the light from that star can be deflected, and that deflection is measurable and can be calculated from the mass of your black hole. So if you can measure the deflection, you will be able to measure the masses and vice versa. Now, the constraints on the abundance from gravitational lensing are much wider. Particularly, you could set it from the mass, you could set your constraints from mass ranges ranging from 10 to the negative 12 solar masses to around 10 to the 3 solar masses. And the primary probe that's used to investigate, or rather to constrain primordial black hole abundance using lensing is via stellar microlensing. So you have the MACHO constraints over here, your EROS constraints, OGLE constraints, Subaru telescope constraints, etc. All of them manage to constrain your primordial black holes at least down to 10 to the negative 2%, 10 to the negative 2 in PBH fraction. So it's also a fairly strong constraint. And then you can also perform gravitational lensing on type 1a supernovae. And the constraints that they provide are fairly looser, but also on a much larger mass range. So those two constraints are those are some of the two constraints that you can consider for primordial black holes. But the most recent ones, and the ones that I'm primarily interested in at least, would be constraints given in by gravitational wave observations. Since gravitational wave astronomy mainly deals with compact object mergers, sky. So compact object mergers observed via gravitational wave astronomy may be interpreted as primordial black hole mergers. The more popular way of interpreting them is usually by astrophysical sources, but there is room to allow an interpretation that is based off primordial black holes. And constraints on the abundance of your gravitational wave observations have been set by multiple teams working on your LIGO Virgo data, and some even looking at your nanograv data. And the advantage that you have in gravitational wave observations is that you can investigate a much wider set of mass ranges. You just need the proper facilities to investigate them. So LIGO Virgo, for example, is usually in the stellar mass range. Nanograv can take you larger. LISA might even take you even larger than that. But in general, the advantage of gravitational wave astronomy is that it's also another probe. Although in general, there are only really two types of constraints that you can set for gravitational wave observations, from gravitational wave observations on your PBH abundance. And that is either constraints from mergers, which are more stringent, because generally you can get one event, and then you could analyze that event. And then you could, based on that event, you could set a constraint whether or not it's a astrophysical source or a primordial black hole source. And the constraints set by your primordial black hole mergers along the mass range of around 10 to the negative 1 to around 10 to the negative to around 10 to the 2 solar masses can be as low as 10 to the negative 3. So that means that out of all of the dark matter that you can have, only around less than 1% of it, way less than 1% of it is possibly due to primordial black holes. However, if you account for accretion in general can loosen the constraints of your primordial black hole fraction. So as you can see here, assuming a monochromatic distribution and assuming a log normal distribution, given this mass range from 10 to the 0 to 10 to the 4 solar masses, you can assume that the fraction of your PBH does get higher if your accretion cutoff is much, much later in the age of the universe. Granted, these are all models as well. So it depends as well on the model. You still also have to verify these models with existing data. And finally, I'd like to close by showing the current constraints over the entire known mass range of your primordial black holes. So you have 10 to the negative 40 solar masses here, up to 10 to the 20 solar masses. And each mass range has its own set of constraints on your abundance, depending on the probe that you're using, and of course, the mass range that you're considering. So for example, Planck measurements constrain your primordial black holes way below the black hole evaporation cutoff. The cosmic microwave background also constrains your abundances to different mass ranges depending on what you're looking at. And these two also have fairly different physical phenomena that can explain them as well. Gravitational lensing generally constrains this area of mass range. So from 10 to the negative 10 to around 1 solar mass. So on and so forth. So this is the entire map of constraints that we are currently looking at for primordial black holes. Now, it's a fairly active field on how you model your primordial black holes, how they grow, how you form them, how they grow, and what are the ways that you can rule out primordial black holes against the more common, less exotic setups such as astrophysical black holes. And in general, what this is telling us is that at least for this region over here, for the region near black hole evaporation, we're fairly confident that the mass fraction of your primordial black holes is constrained fairly tightly down to around 10 to the negative 30. If you move up the mass scale, your mass fraction gets a bit looser. Rather, your constraints on mass fraction gets a bit looser at around 10 to the negative 10. But nonetheless, it's still a fairly active field on trying to find out how much of dark matter and how much of the signals that we are receiving from our experiments and probes is being contributed to by your primordial black holes. So yeah, it's a fairly wide field so far. It's actually really hard to contain all of it as well in a single presentation, but I think I covered most of it already. So that is all so far. If there are any questions, I will be taking them now.
Thanks, Gab, for the presentation. Yeah, we open it two questions from the panel.
You, Gab.
Sige po.
Sige, I can start siguro. Ano kaya gusto mong gawin dito, Gab? Like, what is the...
Actually, sir,
What's
ang
the-
lawak eh. Since initially, sir, I was looking in, kung na-notice you, sir, actually, I was concentrating on the accretion aspects. Since this region over here in general, parang ad hoc ang ginagawa nila sa ano eh, sa pag-model ng accretion cutoff. Since it's generally known that by the time you start your structure formation, so at around redshift 20, redshift 10, accretion is going to be accretion is going to slow down for your primordial black holes. Since stars are starting to form, your gas is starting to be locked up with stars, and your black holes are also going to fall down into your gravitational wells, which is going to hamper their accretion. Thing is, how exactly is it? How exactly does it happen is not that well modeled, at least from a dynamical standpoint, Ren, because at least from my perspective, there will be changes in how much gas your black holes can accrete by the time you reach the area of structure formation. So that's one thing that I'm been considering, although i-reconsider rin namin ni Ma'am Reyna kung if that's going to be a viable direction to take. Another interesting thing to look at would be clustering. Since in general, if your primordial black holes do cluster, there is a chance that there will be more mergers. So if there will be more mergers, that means we should be able to detect those signals. Although the review paper that I cited here kind of makes the opposite argument that if your primordial black holes are highly clustered, then due to dynamical disruption, you might even have less mergers that you can attribute to your primordial black holes.
Pero Gab, dun sa accretion question, so ang idea ba is to sort of improve the physical modeling as one transition to the matter-dominated era? I guess I'm trying to understand. Yeah, I mean, there's huge uncertainties in this subject. I mean, I think you're aware, and I think that's partly what makes it somewhat prohibitive. And this is the worry as your panelist is. Ang dami kasi. So the question is, do you have something specific in mind to sort of modify or improve on? Let's say in the first thing that you identified, which is to understand, sabi mo ad hoc yung magpag-model ng accretion rate as you enter the matter-dominated era. So paano mo gagawin hindi ad hoc yun? What's the, I mean, just the rough idea. What have you thought of? Let's say people haven't done yet.
The past weeks po kasi I've been looking at structure formation on the local scales. So kasi star formation rates, etc. Basically what I'm looking at is the changes in the gas density as your galaxies start forming. So when your galaxies start forming, the stars start forming as well. And that introduces changes to the general local gas density that is available for black holes to accrete. So I'm thinking now, okay, that I guess that's step one, but I'm not sure how significant it would be in changing or in halting or possibly enhancing your accretion depending on the factors laid out there. So basically, I'm looking at star formation rates so far. At least star formation rates at Z20, Z equals 20, up until like Z equals 10.
So you mean to say the current models do not have the star formation rates folded in?
No. They
Since
don't. Since normally they start their accretion at around Z equals 100. And then either once Z10 hits, they either stop it, so that's model 1 of this paper, or they let it extend down the line using what is, well, the Bondi accretion rate. The thing is with the Bondi accretion rate is that it's modeled for very high redshift. And I'm not.
So if I were to read this formula, then if you were to fold in star formation, then
Sa N-gas,
roughly speaking, ba yung N-gas yung magbabago?
oh,
So rather than assuming, so rather than N-gas being dictated primarily by the expansion of the universe, you will have your own dynamical equation governing N-gas.
oh,
Number
at least po within the time period na ano.
What's special about Z equals 10, by the way?
Po?
What's special about Z equals 10?
In general po, from Z20 to Z20 onwards, that's when structural formation is happening na eh. So your gravitational wells are starting to deepen, and your
So
stars are
that's when-
starting to form as well.
Did you say 20 or? Pero yung separation ng models na pinakita mo nasa 10, 'di ba?
Well, roughly po at 10. So dahil log scale po to eh. So around that neighborhood yung separation na nilalagay nila.
Okay, marami pa akong tanong, but I don't want to hog the time. So maybe the other panelists can also ask questions.
Okay po.
Okay lang yan, Ian. Tanong ka pa.
Slide 19.
Mauubos ko. I have about 16 questions listed down. So mauubos ko yung
Okay.
Go ahead, Sir Perry.
Yeah. Ano nga ulit ang plots na to? Ano yung vertical axis? What's
Vertical axis, sir, is the abundance of your primordial black holes at the present time,
okay? Yeah.
based off your accretion models.
Mhm.
Yeah, baka you can elaborate, Gab, kasi hindi mo masyadong
Yes,
na-explain.
parang
yung
ano, yung
cut-off redshifts, yeah, from
Kita
7.
akong white area, tapos ano ba to?
Okay. So
Tapos iba-ibang colors. Ano yan?
basically, yung this plot essentially tells you the upper bound of your primordial black hole abundance as a function of your mass range as well, as a function of your mass. And if you assume that your primordial black holes do not accrete matter, or in a better sense, they don't efficiently accrete matter, then you will have this no evolution line over here. So your primordial black holes, at least in the high mass end, so around 10 to the 2 to 10 to the 4, will be heavily constrained in abundance at present time. That is, you're not expecting that many high mass primordial black holes at present time, if at all, if you do not consider accretion into your primordial black hole evolution models. Now, as you go up, so Z cutoff equals 10 to the equals 15, for example, that means your accretion cuts off at, rather your accretion stops at redshift 15. Then you will have slightly looser constraints on the high mass end. And then as you go up, the loosest Z7, so fairly into, well, hindi pa siya, it's not recent, pero it's around the time where you start having quasars, and when you start having quasars, that's when you can have, like, let's say, the loosest constraints on your high mass end. Since basically from 10 to the 10 to 10 to the 4, you are assuming that the fraction of your primordial black holes as dark matter is on percent level. So around 10 to the negative 1.
Okay.
Or I guess
Okay.
one better way to say it is that 1 in 10 dark matter candidates is a primordial black hole if you take into account accretion that only cuts off at redshift 7.
Okay, sige. Ngayon, yung likelihood of being able to observe a PBH with a particular mass at saka itong frequency nila at saka yung abundance niya, hindi necessary pareho, di ba? Or hindi, kasi baka may constraints associated with what's technologically available, and baka may fundamental constraints.
In terms of technological constraints po, it's dependent on the mass range na pinoprobe ng device mo. For example, LIGO primarily really only looks at stellar mass, compact objects. And if you look at the other constraints set by the other probes, for example, in gravitational lensing, the compact objects that can be probed by, like, let's say, the Subaru telescope is only from 10 to the negative 12 to 10 to the negative 6 solar masses. That is assuming, of course, that those are compact objects as well. And then you have lensing from your type 1A supernovae, which is a probe that can check from 10 to the negative 3 to 10 to the 3 solar masses. So my technological constraint siya, but it's also dependent on the constraints set by the project itself.
Okay.
As for fundamental constraints, I think the most fundamental constraint, at least so far, would be for the evaporation. Because beyond the mass range, below 10 to 15 grams for your PBH, you can't really explore it directly. Well, in the most direct sense na there's a signal from your primordial black hole. And instead, you'd be looking at the byproducts, so changes in the Big Bang nucleosynthesis elements, changes in the CMB anisotropies, etc., that will constrain your PBH abundance.
Okay.
Everything above that, though, it's, kaya nga tumataas yung constraints because nire-refine pa yung measurements on the higher mass end.
So ano yung nag-limit dun sa work na propose mo dito? I mean, you're proposing essentially interesting areas to work on kasi candidacy pa lang to, no? So yung range dito, can you provide, clarify again, I may have missed it, kung bakit ito yung most significant or shall I say most productive direction for you? Itong, tama ba? Yung label mo dito na this work is essentially what you will eventually go to?
Ay,
no,
ano
so
po
this
to?
is different?
Opo. Kinakapadyo
Hiniram
po
mo
to.
lang pala to.
Hiniram ko lang po to.
Okay. So siguro, ang tanong, so ano yung sa tingin mo, what do you think is the best way to go? Which direction? Kasi you cannot definitely not investigate all of this range of masses and the beta, no? So can you discuss on what are the good open problems?
I think, well, apart from the accretion that I've mentioned before, since, well, that's a fairly tricky set of problems in itself, I would like to check on the gravitational wave range, which is actually still fairly wide, but at least I can check my stuff against data. Now, in terms of the physics that can be probed from this, I think apart from accretion, the most interesting place to look at would be clustering of your primordial black holes as well. Since clustering can imply two things with regards to structure formation. Either your primordial black holes are Bosonian scattered initially, and they only start clustering to your large scale structure as they evolve, or your primordial black holes are already clustered. So the large scale structure that forms later on is going to be heavily influenced by the clustering of your primordial black holes because you already have a fairly strong gravitational well in that area. Granted, there are many issues as well with PBH clustering, since then you'd have to check again your CMB for temperature anisotropies, and you'd also have to check your gamma ray background as well, because the heating caused by PBH accretion can be fairly significant in the early universe. You could also check the formation mechanisms, which is closely tied to clustering as well, and closely tied as well to specific models of your primordial black hole mass function, because essentially what you're going to ask now here is, okay, I have this theory of gravity with this scalar field, like let's say an inflaton or something. And if I make modifications to this inflaton, what does it imply for essentially formation, clustering, and the mass and spin distributions of any possible primordial black holes that can form? And if you manage to set that up, then you could go back to your observational constraints. And well, apart from PBH evaporation, you could now check again lensing data. But more importantly, since mas open yung field, you could check it against gravitational wave observations. And so far kasi, in the current literature, marami yung nasa-cite ko rito simply because every time there's a new detection, what the PBH people do is that, okay, what are their masses? Can a PBH binary be considered as a candidate for the event that produced the signal, for the source that produced the signal? So yun yung, well, hindi siya cottage industry, but that's essentially how all of these guys are operating right now, especially sina De Luca. Sila yung nagpasimuno ng, okay, let's take mass and spin evolution into account and see what happens, whether or not the PBH fraction will be relaxed or constrained even further.
Grab, would you mind explaining the basic logic in that process? Naguguluhan ako kasi all this time I thought that primordial black holes are to be constrained by LIGO. So di ba yung PBH distribution, hindi ba stochastic ang signal na yan? Sorry?
Saan po, saan?
No, I mean like when talking about primordial black holes and gravitational wave astronomy, I've always I haven't read the literature recently, but I've always thought that the kind of signal that primordial black holes give rise to is a stochastic signal, and not these coherent.
So Gab, baka you can show slide 18 again, and then explain yung stochastic background and then the constraints from mergers. There are two different constraints.
I think yung pinapa-clarify rin po ni Sir Ian is that kasi I did talk way back then about primordial black holes as a source of the stochastic background signals. But
Wait, no. Actually, the point I was confused about was when one of your slides you said that observed compact object mergers are now interpreted as primordial black hole mergers. What does that mean? Nag, nag, do they also do parameter estimation on? I mean, I don't understand how that actually works. Kasi hindi mo
actually, sir,
naman,
yes,
the
that's
black
what.
holes, they don't really, yeah.
Actually, sir, yes, that's what they do sometimes, especially kina the Cruz Osorio. So they looked at GW19 0521 and tried to pin it to, I think it was either 2 or 3 different gravitational wave possible gravitational wave binaries. So they attributed it to astrophysical, and then they attributed it to primordial black hole as well. And they got their own set of constraints out of that.
Pero hindi ito maliliit na black holes, no? So the idea is you seed some primordial black holes very early in the universe, and then it grows to these large black holes, and then that's the signal that we see.
Yes.
Okay, so
Pwede bang connected question, Ian?
sige.
So on this slide, it shows as 2 shades, no? Yung merger shade at saka yung stochastic background. The way I see it, it seems na sinasabi mo na parang noise siya. So therefore, gusto mo na beyond ka nitong stochastic background, right? Yung signal experimentally or observationally, no?
Yung shade, sir, here, at least for all of the plots, is the exclusion zone. So
yes, because of the stochastic background nga. So it means that the SNR is very low, signal to noise ratio. And you cannot do anything about that. If you have merger signals, then you have signals larger or away from the stochastic mababang SNR. So that's the point that you can identify mergers. Am I correct?
Yes, sir.
And for other gravitational wave data, it becomes more, in a sense, a stochastic treatment because you treat them having noise as well. Tama? And you have to clean it stochastic, to use stochastic method or technique to remove the possible background and clean up the data and have a cleaner data about the gravitational wave that you detect. Tama ba yun?
Well, sir, ganun yung pipeline in preparing your gravitational wave data for analysis. But yung stochastic background na sinasabi rito, sir, is basically what
signal talaga yan.
So it's inherent talaga na may stochastic
inherent
background.
There is an expected stochastic background of gravitational wave events.
Okay, I understand. Okay. And so parang sa atin, this is the blackest of the black hole in a sense na hindi natin malalaman kung ano yan, meron kung sa area na yan napunta yung black hole na tinitingnan mo or object. Tama ba?
This makes the assumption that all of the background is from PBHs. Then the only source, then this is your constraint. But of course, there are many other possible sources for the stochastic background.
And that way, pagka nandito yung dot mo na hinahanap na object, unlikely na makita mo siya talaga. Kasi malulunod siya sa stock background. Tama ba ako? Hindi. Sorry.
No, go.
Hindi naman necessary.
But you don't have a position, location. You do not know where it's coming from.
So you won't know kung ano yung
universe.
mass niya, you won't know kung ano yung omega within that range. Okay. So that's the limitation of your data input. So malilimit din pa pala talaga yung range of mass mo given the F. Okay, thank you.
And then the mergers naman, I think this one, Gab, you can elaborate then. These are from merger rates, like the accumulated merger rates from the surveys. Which is separate pa from the studies that you also mentioned that look at individual systems.
Iba rin po yun. Since at least for the mergers here, so I think consider nilang mass range. Let me try to.
And then maybe these are parang two possible options for your
for exploration.
for exploration, looking at GW observations as parang vis-a-vis assumptions in the your PBH formation and growth scenarios. Is that your parang that's another avenue.
So diba, ultimately the gravitational wave catalog will build towards a more accurate mass distribution of black holes. Ultimately that's really where the field is headed, diba? Like you make more measurements, tapos magi-improve dadami yung population mo, so magi-improve yung distribution. We will get a better probe of the mass distribution as a function of z. So diba, nag-evolve din siya. So ang logic ba ay halimbawa, okay, so this is my assumed say initial mass function for so let me see if I get the logic correctly. So you have a very uncertain initial mass function for primordial black holes in the early universe, and then the idea is that this will evolve and possibly produce or contribute to at least the mass distribution that we will keep on observing as gravitational wave astronomy progresses. Meron ba yun?
Opo.
So hindi talaga siya individual sources, right? It's really a statistical. So that's my point. I'm trying to understand
population. Okay.
The claim kasi that you say that you begin to look at observed compact object mergers as primordial black hole mergers is somewhat bizarre, because you say pwede naman na nag-merge sila later on, diba? Like they could have been isolated black holes early on in the universe that eventually then just evolved later on, right? Ang point ko lang, when we observe them, hindi na sila primordial. I mean, hindi na sila maliliit na black holes, diba? They've already grown, and it's really difficult to know where
to trace the history,
to disentangle,
where this black hole could have possibly come from. So I mean, yeah, I think ultimately where we get the most insight from this is by getting a better sampling of the black hole mass distribution,
merger rates.
Right, and merger rates, and then see whether whatever your proposed initial mass function is, and whatever your proposed evolutionary mechanisms for the primordial black holes are, whether those are in fact consistent with the mass distribution that we will eventually. We actually have a mass distribution now, and it keeps on getting better. But I think that's a key idea. Kaya sort of this is becoming important again.
Yeah, that's an avenue. I guess just
So
what he said, because there also are studies like that. So for example, just parang what is the likelihood that this is from a primordial black hole merger?
Right.
If the spins are high, because the parameters are from the parameter estimates you get spins that are high, then the probability that it's a primordial black hole becomes very low, because we know that initial spins are low, unless there are mechanisms that increase the spin. So may mga
enhance the spin.
Ganong exercise naman of saying na whether this is I guess yun nga, it's a different question of is this system astrophysical or primordial? What are the relative likelihoods of that? But that's another avenue nga. But the thing is, interesting din siya in the sense that for data analysis, because there are priors that are assumed in the Bayesian parameter estimation, and the usual assumptions are that they're astrophysical. Then you get your parameter estimates. So there are also studies where you apply priors that are consistent with primordial black holes, and then you see the difference.
Gaano kalaki yung
And that's
changes
the study.
on those priors?
Sige, baka Gabby can. Or,
Yung pa ako gano'n
Uncertainties ba yan, Ian? Hindi changes? Uncertainties ba o changes?
So yeah, kasi when you make a parameter estimation, so when you do a Bayesian analysis, you the usual assumption is to exclude primordial black hole origin for the constituent masses. So I guess ang question ko is, so suppose you include it, and so you change the prior somewhat. How large are the changes in the priors, and therefore how large are the changes in the estimated parameters?
May people,
are they significant? Like, can we get, for example,
Uncertainty nga.
exactly. We have quoted masses and spins. I mean, do these significantly change if we start considering primordial black hole origins?
That's actually ang tanong Ian is called sensitivity ng model.
But of the Bayesian of the parameter estimation.
I think so. I can actually link to you that exact a paper that actually tries to answer that exact issue, but I haven't checked apart from the claim that the paper made that there are fairly significant changes when you consider priors that are favorable for primordial black hole models.
So I have a curious question. Matagal na kasi ang primordial black holes. I mean, this predicted even Sina Bernard Carr way before even I started grad school. Tapos naging laos na siya. I mean, Reyna would know this. I mean, naging laos siya for a while. I think during our grad school time, hindi laos yung primordial black holes. Kasi di ba, it was proposed as a candidate dark matter. Candidate dark matter siya, ganun yung pinaka-exciting avenue for primordial black holes at the time, or before we entered grad school. Bakit sikat na naman siya as dark matter? I noticed this is a dark matter review, and it's 2021. Would you walk me through, as somebody who has read the literature more thoroughly than me, bakit siya sikat ulit? I mean, so di ba nalaos siya, so presumably nalaos siya because di ba, hindi na siya pwede. There's very strong constraints against it. Right. So why is it now all of a sudden being entertained again?
I think, sir, it's thanks to gravitational wave astronomy. But
that's a different kasi. So that's what I was thinking, but that doesn't make any sense, at least logically. I mean, that I would understand that. So Sasaki-san's review is certainly, I think, I think topical. Kasi nga, the idea is, for sure, gravitational wave observations provide important constraints on primordial black holes. So I understand that, but the dark matter thing is what I don't understand. Bakit siya sikat na naman as dark matter?
Well, kasi sir, even with like Green's review, they really, apart from lensing, which is, I think, actually they're already trying to poke at this is possibly a primordial black hole. It's really looking at gravitational wave observations as, okay, maybe we can use gravitational wave observations to provide different or more stringent or even less stringent constraints to your primordial black hole abundance. So sir, parang other way around na yung nangyayari na, okay, we have a probe for black holes.
So it's not as if sinasabi na, oh, let's just ignore all the constraints in the past.
Yes, sir. It's more of let's constrain it further.
For PBHs to be dark matters. It's not like we are ignoring them. And then, okay, sige, kasi sumisikat siya sa gravitational wave, let's begin entertaining them again as dark matter.
Yes, sir. Yes, sir. It's something along those lines.
Well, so wait, sorry. So you're saying it is or it is not?
It's yes, sir. Actually,
ang kwento was, so okay, so it's a viable dark matter candidate. Tapos constraints, hindi na siya pwede as a cold dark matter particle. Okay, kasi masyadong malakas. It became slowly very disfavored by the community. And then ngayon, okay, may gravitational waves. So, okay, so I can understand gravitational waves as a probe for, uncertainties to primordial black holes. So that yeah, I have no question about that. That's, I think, a very solid line of inquiry. But then why are we now reopening the question of primordial black holes as a dark matter candidate? What did we do with all the other constraints that existed in the past that made it a disfavored idea?
I think,
As
sir,
dark matter, not as gravitational, not as a source for gravitational waves, as dark matter lang.
I think, sir, one of the things that we need to look at as well is like if we look at previous constraints, the mass ranges that they consider, for example, like let's say here in the evaporation constraints, only constrain it confidently up until like 10 to the negative 16 solar masses. Then if you look at gravitational lensing, your constraints at the high mass range are actually fairly weak, or at least they're fairly loosely constrained compared to the constraints that you have in the lower mass range. So what they're trying to look at here is, okay, we've beaten to death the constraints for very, very small primordial black holes. But if you look now at the GW observations, okay, it's a smaller mass range, but it's also at an order of magnitude larger than all of the other previous constraints as well. So really, I think it's also just a matter of exploring or trying to constrain the larger possible PBH mass ranges that you could check. Since dito, in this paper ni Nakapadya, like the 10 to the 0 to the 10 to the 20 range is very, very loose. And even in the papers that explore primordial black holes as sources of gravitational waves, their motivation is always dark matter. So trying to constrain its abundance relative to dark matter. So yun, sir, actually yung nangyayari at least sa literature.
Yeah. So I actually have other questions. More theory related. So di ba yung sinasabi mo merong gamma ray background na hinahanap?
Yes, sir.
Saan kagaling? Pwede pa kapaliwanag kung saan galing yung gamma ray emission?
Well, sir,
Evaporation?
so back to Hawking radiation. So as it emits Hawking radiation, eventually, once it fully evaporates, it bursts into gamma rays. So for primordial black holes with the mass
Malinaw
range,
ba yun?
What?
I thought the whole question of the end state of Hawking evaporation is a very, very open question.
well, yung assumption, sir, if the byproducts are gamma rays, then that's one thing to look out for at the very least.
No, but why gamma? that's the key thing. It's a very specific high energy particle. Why gamma?
That's, sir,
Kasi,
I'm not.
Gamma is associated with like really really high frequency, right? So I would have thought that right. So in normal Hawking radiation, you have a frequency that's basically it's a thermal background, right? So the thermal emission, the emission is thermal, and the thermal, meron kang black body distribution that's characterized by a given temperature, right? So I would expect that the primary emission channel would be dictated by that temperature. So, and as the black hole becomes closer and smaller and smaller, nag-increase ba yung temperature ng black hole? I mean, you have a Hawking evaporating black hole. It becomes smaller and smaller because presumably emitting radiation, so therefore it's losing mass. So the temperature, what happens to the temperature as that happens? Does it increase? I guess, how does it start emitting in the gamma?
May kinalaman ba sa spin yan?
Wala nga spin yung kanila eh. Kasi, well,
zero spin.
that's actually another question that I have, but I'll get to that in just a bit. Pero yung tanong ay, so you keep on emitting, right? So hindi naman gamma initially. Kasi I would say this is a fairly low temperature black hole. I don't know. Hindi ko nga alam. Depende sa mass distribution siguro ng primordial black holes. Then it keeps on emitting, right?
So
And
ang
then
question is, what is the mass dependence of the temperature of the
Well,
Hawking temperature?
inverse.
1 over
Hindi, kung saan galing yung gamma. Tama iyan. No?
Yeah.
Why
So
gamma?
the mass becomes smaller and smaller, tapos nag-increase yung temperature larger and larger. So that's the idea.
The frequency.
Pero ang question mo, Ian, is ano ba yung source ng gamma ray? Is it temperature? Thermal ba yun? Or something else?
Well, so hindi, alam ko yung sagot doon kasi yung quantum fluctuations naman talaga yung radiation. So basically, it's the vacuum itself that's physically you're really generating black body radiation around the vicinity of the horizon. So well understood naman yun. Ang ano ko lang is I think there's serious doubt about the end state of Hawking radiation. I know this because I was
it
really
requires a model of quantum gravity.
Exactly. So I know this very well because I was embarrassed by this a long time ago. Sabi ko, hindi ba magiging flat space lang? When a black hole evaporates, it just becomes flat and then there's nothing. Maawa yung kausap ko. I mean, how do you know? I mean, we don't really know what happens when the black hole becomes very, very small. So I don't know. And the point is, there are assumptions in the calculation of Hawking that require like adiabatic evolution, slow evolution that will no longer hold when when you push this black hole, this small black hole to its extreme. Hindi nagagana yung picture ni Hawking. So we really don't know anything about the end state of
ano ba yung
The question is yung
ba yung
assumption
range
nitong
ni
gamma ray
Senator?
background constraint?
Ano bang range ng Hawking radiation? Sorry, wala akong alam dyan. Pero ano ba yung typical na range ng wavelength niyan?
So, well, ano naman siya? It's basically black body. So black body, ano lang siya? Distribution lang siya. Na-centered dun sa Hawking radiation. Hawking temperature.
Hawking temperature.
A Hawking temperature is inverse of the mass nga. Right? So maybe I can imagine, since the mass is going very, very small, lumalaki yung temperature ng black hole to the point that at the end, halos gamma na yung emission niya. Ganun ba yun?
So yun po yung
Pwede ba?
extrapolation at least. Pero yun na, it's also reasonable kasi ano po for example, dito kina Kapadya, even with the primordial black hole evaporation taken as a general standard, they still actually did this kind of probe because we're not even sure if the products of or rather, we're not even sure if the primordial black holes in this region have evaporated at all. So my assumption rito na, okay, below this, your PBH evaporates already. But as to how it does it, at least yung sinasabi na Kapadya rito, assuming that they don't evaporate by present time, these are the constraints that we would expect on the gravitational wave background.
From the stochastic gravitational
From the if you're using PBHs as the source of that stochastic background.
Parang tanggap ko naman yung explanation. Yung isa pa, yung chi formation, yung the spin at the formation, tinanong ko yan. Let's see here. Where does the prior come from? This notion that formation does not have significant spins at the beginning. Ano yung core physics dun? I know this has been quoted many times. I've also heard this from other speakers, but I'm too embarrassed to ask. But since I'm now a panelist, I'm not embarrassed to ask this anymore. Bakit ano? Bakit? Hindi ko talaga alam. What's the underlying logic for why we expect there to be very little spin, very little asphericity in the initially formed primordial black holes?
I think the assumption starts from the fact na, well, radiation dominated yung isang factor na nilalagay nila rito always when stating that, okay, low asphericity. I think it's also something like the gravitation, the existence of the overdensities in general throughout the universe, at least at time of formation, is fairly rare. So yung neighborhood nila, at least, is not going to induce that much torques on your overdensities as it starts accumulating matter energy. So,
sorry pakiulit. Nandito lang na.
So, in the radiation-dominated era, at least with most models, with the common models, ang nangyayari is that the formation of your overdensities is considered rare, at least for a local neighborhood around that overdensity. So in general, there will not be any other large densities of matter that can tug on your overdensity that will give it an additional torque as it accumulates matter. So parang spherical infall lang lahat yung naging expectation sa formation during the radiation-dominated era.
But isn't that strange though? Kasi yung sagot, the result here that you quote, like chi formation, depends on the PBH power spectrum.
Oh.
But in the argument that you just used now, you're assuming something about the. Wait, aren't you implicitly assuming something about the power spectrum in saying that the formed overdensities are fairly dilute? So, tama ba yung pagkaintindi ko? Parang, so you form, and then there's not much anywhere else. So,
parang sir, you usually form in isolation. At least if you don't assume clustering, significant clustering. Well, in isolation relative to other overdensities.
Well, in any case, does that uncertainty strongly affect merger rates and the future mass distribution?
Actually, sir, this parameterization and this mass function and the initial spins here are pretty much the groundwork for actually developing a merger rate for your primordial black hole, for your primordial black hole models. So if you can
akala ko kasi
specify.
Akala ko lang kasi yung assumption before, people always assume sphericity kasi mas madali yung dynamics. Siyempre, di ba kapag nagdagdag ka ng spin sa primordial black holes mo, magiging mas complicated yung pag-evolve mo in time because then you have two spinning black holes with misaligned spins and angular momenta that are not even aligned with their spins. Pwede kang magkaroon ng kicks, pwede kang magkaroon ng kung anong three-body dynamics which are quite difficult to model. So I've been under the assumption na parang this is a simplifying assumption.
Well, you could think of it. Well, you could think of it as that, sir. Pero as far as I can tell, there is a physical motivation as to why. the PBHs, at least in radiation-dominated era, are considered to form with fairly low spins. And then they only start screwing spin as they start gaining more mass and matter. Actually, I only showed here the accretion rate, but there is...
Bondi hole yan, walang spin dependence yan eh.
walang spin dependence po. Pero, as it accretes matter, so as your primordial black hole accretes matter, nag-change rin yung mass function mo, pati yung spin distribution mo eh. So this is like an initialization step for most people doing parameter estimation on primordial black holes, at least in relation to gravitational wave events. And then from here, they'll evolve it using Bondi Hoyle and in general how your spins evolve as well. And then they'll calculate a merger rate at present time. Or rather, they'll first calculate if your PBHs will accrete enough matter to be considered within the range of the event window of your detectors. And then they will also calculate if they will accrete enough if they will merge in time as well to be detected at present time using parameter estimation.
I have one last question, Gab, kasi it's related to the first question I asked you.
Sige po.
How, ano yung entrada mo? Like, what do you want to do? And sagot mo nga was to sort of fold in stellar formation into the evolution of accretion rates. So if we go back to your page 11, I think that was where you showed us a model for, this one. Sige, walk me through nga. So, pwedeng paintindi ng plots ng konti. So,
Sige.
you have a mass increase, accretion rate that increases rather sharply for low mass primordial black holes. Tama ba? So that's in the this sort of dark halo phase, nag-increase siya for these relatively low, well, actually medyo mabigat pa rin, pero nakikita mo yung increase dito. So may basic physics ba yan? What explains this increase of the mass accretion?
Basically po, it's just as your black hole accretes more matter, it becomes more efficient in accreting that matter. Up until a certain point where naging super Eddington yung kanyang accretion rate niya, and it becomes really efficient na in actually eating up, in actually obtaining matter for itself.
So Eddington tong limit na to.
Opo, Eddington yung limit. Normalized to Eddington po yung accretion rate din.
Okay, so super Eddington na tong lahat. Kasi
at least po past one.
So bakit siya bumababa? So okay, so it becomes more and more efficient the heavier it gets. Then what?
And then once you pass, like let's say a critical redshift cutoff, the general physical motivation, the general physical argument is that stars start forming, so your free gas gets trapped into your stars.
Okay, so akala ko ba hindi pa folded in ang star formation dito, sabi mo?
Well, hindi po folded in yung details po of the star formation, pero parang
pero may star formation na dito sa model 2.
Hindi. Yung sa cutoff po na kino-consider. Na yung kino-consider nila na cutoff na okay, dito na nangyayari lahat yung reheating, gas reheating, star formation.
You're
galactic
referring to
formation.
model 1, which is just sharply decreases at z less than 10.
For this paper, model 1 would be sharp decrease,
Mm-mm.
yung maging assumption. Now, model 2 assumes that there is a decrease, but it's not going to be as significant as what they assume in model 1, which is a complete shut off of completion.
And you're
So what-
thinking of adjusting that, parang that the filling in the gap between model 1 and model 2 as as a function of yun nga, yung star formation and structure formation.
So I
Para
guess yung
connecting
curious
to
ko
that.
lang,
Para
what's
to that
driving the
phenomenon.
decrease? What's driving the decrease in accretion in model 2?
In model 2 it's just the expansion. Since yung the redshift dependence of model 2 is just N gas going
down.
yeah.
So ang idea lang is
gas
So in-
equals
so itong decrease niya, that's just characteristic of the expansion. So this
Opo.
scale factor lang yan.
scale factor lang po, more or less. Since generally po, ito yung ginagamit nilang number density. It evolves in time.
So is the idea that model 1 and model 2 parang bracket the scenarios, and the realistic scenario is somewhere in between?
And it would also depend on the neighborhood that you're considering.
Mm-mm.
Although more or less
Yung
the
model, so yung model 1 shut down lahat. Shut down and
shut down po lahat.
sharply.
Essentially yung hot point evolution at that point.
No more accretion.
No more accretion. Pero
Tapos yung
dito,
consideration rin po rito is that the effect of second generation mergers, like yung merger of a merger na, is they're not taking that into account, at least for this paper and other papers that I've read that attempt to incorporate accretion into the mix.
Accretion naman to, Gab. Oo. Hindi po outside the, I mean, iba pa yung merger. No?
Okay.
All right. It's
Happy na.
it's around 3:30, so we can have a last call for questions. Sir Perry, you're on mute.
Okay na. Readiness to begin lang naman kasi yung ina-assess natin. Tagal nang nagsimula niyan.
Okay na rin sa akin.
Okay, thanks,
Okay.
John Gab.
Ay, nasan yung form?
Gab?
Okay,
Gab,
dapat
yung form.
kay Ina or kay Gab.
Wala pong form na binibigay sa akin si Sir Witz.
Sandali lang.
Dapat-
Parang ganito rin ang
Record din ba
dati
tayo
kay
na
Kimber,
mag-picture?
naghanap ako ng form.
Dapat ma-accomplish to before 24 hours.
Yes.
Ay, by the
Sige.
way, pwede
Okay,
natin-
sorry, hindi kami ready.
we can shut off the YouTube.
Sige, let's turn
Record.
the recording
Off
na.
record na tayo.